Good evening, all of you. Welcome to our almost a monthly presentation now. My name is Pradeep Kumar. I am the Oregon Chair of the IEEE Communication Society. The function of the grassroots societies is to inform people of what's going on and what are the emerging areas of technology within that particular discipline, whether it's a computer society, the communication society, or whichever we are. So in Portland, there's about a dozen active societies. So we have meetings relating to each of those chapters each month. Our moderator today is Dr. Rath Verathambi of Intel Corporation. He has been a distinguished speaker in the past, and recently I heard that he is now, can I announce that? You're now a IEEE fellow, right?
Yeah, sure.
So congratulations, Raf. And he recently also accepted, with some arm twisting, to become the vice chair of the Oregon Communication Society. So, right. And with that, I will hand over to our moderator, Dr. Raf.
Thank you, Pradeep. All right. I'm very excited to introduce our speaker, Mohammed Adik Guzman. I'm sorry if I am not presenting saying it right. So he is professor at the University of Oklahoma. He obtained his master's PhD in electrical engineering and electronics from the University of Manchester, and he holds the Edith Kenny Gaylord Presidential Professorship in the university in the School of Computer Science at the University of Oklahoma, and he is currently the editor-in-chief for the Journal of Networks and Computer Applications, and he was the founding editor-in-chief for the Vehicular Communications Journal, and he has been in numerous editorial boards as well. And he has been very contributing to many organization conferences like Communication Society flagship conferences, Globecom and ICC. A lot of contributions that he has done to IEEE and ComSoc. And Mohammed has received numerous prizes and awards. Just a few, he received the IEEE Communication Society Fred Ellersick Prize and the IEEE Distinguished Technical Achievement Award and IEEE Satellite Communication Technical Contribution Award and NASA Group Achievement Award and many other. And he has also, he has more than 350 publications, and his current research interests are in the areas of transport protocols, wireless and mobile networks, ad hoc networks, satellite networks, power away networking, and optical communications. And his research has been funded by NSF and NASA, U.S. Air Force, Cisco, Honeywell, Oklahoma Department of Transportation, and Oklahoma Highway and Safety Office. S- uh, with no further ado, let's welcome Professor Mohammed Arik Guzman, and look forward to his wonderful speech. One thing, like in the past, we asked everybody, if they want, if you have any questions, put it in the chat box. Then the moderator or the host can read those questions to the speaker. This time, we allow the participant to directly ask the question, so you can ask questions as interactively, or you can keep the question at the end. If too many questions comes, then we will see we need to do anything about it. Otherwise, you can ask questions in the middle. All right, without any other further ado, let's welcome our speaker.
Thank you, Rath, for the nice introduction. And thank you both to Rath and Pradeep for inviting me to this program and the Oregon chapter. I've never been to that area, but it's a real pleasure to be sharing my research results with you guys. And hopefully, when the COVID situation is over, we might be able to travel. And hopefully, one day I'll land up in your area and give a talk face to face and shake hands. So anyway, this talk is about connecting the space assets to the internet, and this most of this work has been funded by NASA for quite some time. And I'm going to share you the fundamental stuff or the basic stuff we've been doing to connect the assets or space assets to the internet. By internet, I mean the terrestrial internet. And I'll discuss some challenges and some solutions we developed. So one of the advantages of satellite networks over terrestrial networks, which we are used to, is a ubiquitous coverage. Like Wi-Fi is limited to buildings, telecom networks or cell phone networks are limited to cities, highways. But when you go to mountains or you go to oceans, there is no coverage like Wi-Fi or cell phone coverage. So here are some examples. For example, when you are in a let me get the laser pointer. Okay. For example, when you are in a ship in the ocean, or you are flying up in the sky, or there are soldiers in the battlefield, there is no coverage, either from Wi-Fi or from cell phone. But satellite has a ubiquitous coverage. It covers oceans, it covers mountains, skies, deserts, battlefield, everywhere it's covered. So that's a big advantage of satellite networks. And it's pretty reliable. It does not break down as often as other networks do. So in terms of using satellite networks, a lot of the objects are remote, like they could be in the desert or they could be in the forest, and they could be dispersed over a wide geographical area. For example, a few ships scattered over the ocean, so they are very dispersed. They are not in one place that you can have a small coverage. It has to be wide coverage. And a lot of the places are inaccessible, like in the deep forest. You cannot set up a network because you cannot even access the network. So in those cases, satellite is one of the promising networks. And the global coverage is in the sense that you have one network which covers every country. So that's a big advantage in contrast to cell phone coverage, where it varies from country to country. So the single platform advantage of satellite networks gives it a distinct flavor as compared to other types of networks. And recently we have been talking about Internet of Things. So let me put this context in the Internet of Things. Internet, basically the thrust is to connect everything to the internet. Whatever the device is, whatever the object is, everything has to be connected to the internet. And if you look at the satellites, if you look at the space assets, these can be considered as devices up in the sky, and we are trying to connect them to the internet. So it fits in pretty well with the definition of IoT, that we are connecting these things, which are the devices or the space assets in the space, which we want to connect to the internet. So if we look at the IoT market over time, it's so this is the total market of IoT via satellite. We're not talking about other networks like Wi-Fi or cell phone towers. These are satellites. And satellite is not a huge market, but you can see a steady rise in the predicted revenue in the satellite networks. It's not a big market in the sense that too many people don't use it. Most people use cell phone tower or Wi-Fi, that sort of networks, but these are used by people who are in very remote places and they want global coverage, like DoD, maritime. Uh, if you want to detect forest fire, if you want to monitor the earth for hazards, you need this sort of networks. So terrestrial networks do dominate the current scenario, but IoT through satellite will experience a growth over the years, and it's not going to be an exponential growth. It's going to be more or less linear growth in the coverage. If we look at satellites or spacecrafts, these are put in orbit and they contain devices for collection of information. And depending on what sort of information you want to collect, the satellites contain different types of devices. We can call them sensors as well, because they are sensing something and collecting information. This is an example of a satellite called Juno, and it has science equipment. So it has energetic particle detector instruments. There are radiometers, there are magnetometers, all sorts of equipment are there up in the satellite. And that's why the satellites have been sent up in the sky with all these devices, so that they can collect information from two places. One is down from Earth, another is up in the space. So these satellites, a lot of them just look down onto the Earth and watch for hazards, watch for rainfall, watch for fires, or whatever it is. And there are some satellites which are looking up in the space and trying to explore the space. We don't care about all those missions. Whatever the objective of the mission is, they have equipment which are collecting information, which are collecting data, and that have to be transmitted down to Earth for the scientists to analyze. So is it possible to connect these onboard science equipment to the internet? That is a question we have to answer, because currently these devices are sending data from the satellite to the Earth, mostly through dedicated lines. The reason is dedicated lines is those lines are only used by the devices which are up in the satellite. But as we know, if we can connect them to the internet protocol, then it will enable us to run a lot of other applications. A very simple example is a dumb telephone where we could only talk. And then, of course, after some time, we were able to send text. And that's all we could do with a dumb phone. But after the smartphone came in, look at what we can do with a smartphone. I mean, the smartphone has replaced almost all the daily life stuff we used to use. It has replaced the camera. It has replaced the GPS. It has replaced the calendars and all sorts of MP3 players. It has replaced almost everything. And it was all possible because we connected the phone to the internet. That was one of the reasons we could develop all these applications. So if we can connect all the devices up in the satellite to the internet protocol, then we will be able to have lots and lots of applications. So these devices which are up in the satellite, they can be made IP addressable. That means each of them will have an IP address as a node in the internet. Now I don't call it anymore the terrestrial internet, because the internet is going to be connected to the space. So I'm going to call it just internet. And these devices which are up in the satellites, these could be sensors, radars, telescopes, weather equipment which are observing the weather. And there are actually missions which are also going around the Earth to detect fires. And as I said, these are mostly connected by dedicated lines, and we want to connect them to the internet protocol. One of the issues that comes up is the mobility of these satellites, because when these satellites are rotating around the Earth, they are mobile as compared with reference to the Earth. I'm not talking about the geo satellites, which are of course stationary as compared to the Earth, but the other satellites, the low Earth orbiting satellites or the medium Earth orbiting satellites, they are actually rotating around the Earth, and they are connecting to the ground stations on the Earth, which means as they're rotating in their orbit, they are connecting to different ground stations at different times. And when they're connecting to different ground stations, the equipment which are on board also have to be handed off between the ground stations. So mobility is an issue whenever we want to connect the devices up in the satellite to the internet protocol. And usually these devices on the spacecraft will be connected to onboard LAN, which will be connected to the ground station on the Earth. So this would be similar to the spacecraft or the airplanes. When you are on the airplane, we are connecting to a local onboard LAN on the airplane, which is connected to the ground station via satellites. That's what happens when we access internet from the planes. So connecting the mobile devices to the internet requires mobility management, and that is one of the topics of the discussion today. So let's see where all this mobility comes from in a satellite network. There are mainly three types of mobility I'm going to discuss today. One is the inter-satellite handoff, which means as these satellites are rotating in orbit, they come close to each other and then they connect to each other. And so the connections between the satellites have to be made, and sometimes they will break because they are far away. The other type of handoffs happen when the satellite is being used as a router, or the satellite is acting as a mobile host collecting data. So let me discuss the first one out of the three. In this case, this is the red is the orbit of the satellite, and you can see a couple of satellites over there. And the satellite was connected to the ground station. When the satellite moves away from the ground station, a new satellite comes over the ground station. So you have to switch the connection from the first satellite to the second satellite. So this is an inter-satellite handoff because the connection has been handed off from the previous satellite to the one we just came in over the ground station. The second case I will discuss is when a satellite is being used as a router. So think of a scenario where this lady is somewhere in the middle of the desert or in the battlefield, somewhere where there is no internet connection from the traditional networks. The only way she can connect to the internet is by connecting to the satellite overhead, and the satellite will in turn connect to the ground station. That's the only way she can access the internet in a place where it is very remote. But these satellites we're talking about are LEO satellites, and when this satellite moves away and she's under the coverage of a different satellite, then she has to reestablish a connection, and it involves a handoff from one satellite to another satellite. Let me talk about the third case. In this particular case, this satellite is collecting data. Whatever data is collecting depends on what device is being used, and that data is downloaded to ground for the scientists to analyze through the ground stations. Now these are LEO satellites, so eventually this satellite will move away and it will connect to a different ground station. When it connects to a different ground station, it has to reestablish a connection. And as we know that IP address is tied to a particular location, is tied to a particular location. So in this case, when the satellite moves from the first ground station to the second ground station, it has to get a new IP address and, of course, reestablish a connection. Now, when it gets a new IP address, we do not want the previous connection to be terminated because it might be downloading terabytes of data, and we do not want to restart the transmission of the data from the beginning, because after some time again it will go and connect to another ground station. So we want to maintain the continuity of data by maintaining the connection. So that is the third case of mobility up in the sky. So I have just discussed three cases of mobility, but in addition to those, there are lots of handoffs going on in the space, and I have not even discussed the handoffs that take place in the physical layer. Like there are spot beam handoff and link layer handoff. There are different types of handoffs which happen in the space, and this is because the satellites are all moving around the Earth. That gives rise to all these handoffs. So the question is mobility management. How do we do mobility management up in the sky? And mobility management is not a new thing. This happens every day in the terrestrial networks as well. Let's see how the US postal system handles mobility. So when we are living, so this is a case of a person who is living in New York, and this is the in New York, and then this person moves to a different place, and this person goes to the New York post office, and tells that I have, and fills in a form like this, says that I used to live here and I moved to the second address. So what the post office does for a few months is, whenever a letter comes to this person at this address, post office does not deliver the letter to their address, but it forwards that letter to the new address, where the post office there receives the letter and delivers it to that person. So the way US postal system handles mobility of people is by forwarding. So the key word is forwarding. And that sort of concept has also been used in the internet protocol called mobile IP. So here is a scenario where there is a home network, and this laptop, which is a mobile device or the mobile host, it used to be in the home network. That's where it usually connects to. And because of mobility, the mobile host actually moved out of the home network and went to a foreign network. And how do we handle this mobility? Because when it goes to the foreign network, it has to get a new IP address. So this protocol, the mobile IP protocol, handles this sort of mobility by the principle of forwarding, exactly the same way as the post office does it. So when the mobile host moves from the home network to the foreign network, it gets an IP address from the foreign agent. So foreign agent is one of the devices or the network devices we need to implement the mobile IP protocol. So it gets an IP address from the foreign network, and then it tells the home network that I have moved to a foreign network, and here is my new IP address. So that is a location update that is sent to the home agent, and the home agent is a networking device which will intercept the packets coming from any other node which is sending data to the laptop, and the packet is going to be interrupted instead of being delivered to the host because the host is not there. And this is the registration procedure that just happened with the location update. The packets are going to be intercepted by the home network, encapsulated, and then forwarded to the foreign agent. And the foreign agent will decapsulate the packets and deliver it to the mobile host. So as you can see in this mechanism, the packets are being forwarded from the home agent to the foreign agent, which is delivering the packets to the mobile host. So it is very, very similar to what happens in the US postal system. Now, when the mobile host sends an acknowledgement or wants to send data to the correspondent node, that data can be sent directly from the mobile host via the foreign agent through the internet to the correspondent node. It does not have to go through the home agent because the correspondent node did not move. In this particular case, we had to do all this mechanism because the correspondent node does not know that I have moved from my home network to the foreign network. So that is transparent to the correspondent node, and that's why the packets had to be forwarded, just like in the US postal system. So this sort of protocol is a standard protocol in the terrestrial network. This is nothing new, and it has been tested, it has been standardized, but people don't use it much because we don't need that sort of mobility to be handled. So and after this protocol was developed, there were a lot of drawbacks we found of the base mobile IP. I call it base mobile IP because I'm referring to the original protocol, and there have been a lot of enhancements or individual solutions which have been proposed for these different drawbacks. And I will tell you why those things don't work very well as soon as I discuss these issues. So one is, in order to use the mobile IP, we need to change the internet infrastructure in the sense that we have to have a home agent in the home network. We need to have a foreign agent in the foreign network. And hardly nowadays in the networks people have that, home agent and foreign agent, to do mobile IP. So if I move from Oklahoma to another place, in order to run mobile IP, I have to tell my university to run a home agent, and whichever hotel I'm staying in, I have to tell the hotel people or the network people there that you have to run a foreign agent. So I have to have these two agents in the infrastructure, and it does not just work with the normal internet infrastructure. So that's one drawback of this method. It's not, it doesn't work without adding more components to the internet infrastructure. In order to hand off from the home network to the foreign network, we have tried this in our lab, and a lot of people have tried it. There is approximately 10 to 15 seconds of delay to hand off from the home network to the mobile host. And during this time, packets coming to the home network have to be buffered, or if the buffer is full, they are going to be lost. And of course, the latency I just mentioned. So there's a high handoff latency and a possibility of packet loss. The routing is very efficient. Whenever there's forwarding, the routing is very efficient. So the home agent, the foreign network could actually be very, very close to the correspondent node. But when the correspondent node is sending data to the mobile host, it is being forwarded from the home agent to the foreign agent, which is actually very, very close to the correspondent node. It could have directly sent it through the internet, and it would be much faster. So the path is very inefficient because of forwarding. Then the base mobile IP does not work very well with a lot of the security solutions like ingress filtering. And of course, as I said earlier, there are individual solutions to all of these individual problems. And of course, there are survivability issues and manageability issues, because if the home agent dies, then all communications are gone. You cannot get any forwarded packet. Now, people have developed individual solutions to all of these, or a lot of these. When you put all those solutions together in the base mobile IP, there are a lot of performance issues. So most people will find a way to solve this issue and show that the performance increased. And some people will come up with a solution for this one and say that, yeah, we solved that problem with a slight degradation in performance. But when you put all of them together, it's extremely hard. There is no one solution which solves all these problems together. And that makes it very difficult to implement all these individual solutions and make them work together efficiently, because all these different solutions have been developed by different people. So coming back to NASA's thrust in managing mobility, they want to connect whatever assets they have in the space to the internet protocol, because a lot of the projects could benefit by connecting the devices to the internet protocol. So one of the projects, for example, is a global precipitation measurement, how much rainfall there is. And there's a project called CANDOS, which will connect the spacecrafts with all the space assets to the ground and ground networks and everything together. So there are projects like those. So and there are a lot of other projects, in order to test mobile IP, whether mobile IP can work in this sort of environment, they have been working with Cisco to develop a mobile router. Because as I explained earlier, whenever these satellites are mobile, you need to have a router, onboard router, and that has to be a mobile router, because that router is actually moving. And there are other projects also NASA have been looking at which could benefit if we could connect all the space assets to the internet. And these are some of the projects I just mentioned. So their objective was and still is to develop a very efficient mobility management scheme which will work in the space environment. It has to be very, very secure. It has to do seamless handoff. That means the users should not be aware of the handoffs taking place, and it should be applicable to both satellite networks and probably the terrestrial networks as well, so that the investment and the technologies that will be developed can also be used by a wider audience or more people, if we can make it to work with the terrestrial environment also. And the second objective, of course, is to be able to, so that the data downloaded from the satellite networks can seamlessly be transported to scientists who are connected to the terrestrial internet. So that gives rise to the motivation for a new mobility management protocol in the space. And the objective was, can we come up with a mobility management scheme which will not need additional hardware or software. It will in the core internet. When I'm saying no new hardware or software, in the internet infrastructure, because the internet is so big, it is almost impossible to change anything over the internet infrastructure. It's very, very difficult. And just for NASA's application, people are not going to do it because their application is very limited. So these applications, which are used by not only this mobility management, any application used by DoD, applications used by NASA, these are mission agencies. The number of people using them is small, but their impact is large. So they want to make sure, or they want one of the objective is all the multi-million-dollar investment to develop a technology. If it can be used by general public, that would really help. And there are a couple of successful examples. One is the internet itself, which was developed by DoD. Second example is the GPS, which was developed again by DoD, and then everybody uses it all the time nowadays. And these are two investments government made, which are used by almost everybody in everyday life. And there are lots of other applications as well. So the objective was to develop a protocol which would not need a new hardware. The latency and packet loss rate would be very, very low, and it would remove the data routing problem, the inefficiency in the data routing. It will work with the existing security mechanisms smoothly, and it will be easy to manage and survivable, so that if any part of the network blows up, it still will work. And of course, it has to be suitable for the satellite networks. So we came up with a proposal while NASA was investigating the mobile IP, or the mobile IP for the space environment. We said, why don't we develop another protocol in parallel to your investigation of the suitability of mobile IP for satellite networks? So we came up with this protocol. And we, first of all, we looked at what are the issues in mobile IP due to which we have all those problems. Can we find a single problem spot? And we found that the location management and the handoff, these are two different things in a mobile network, and they are actually coupled together in mobile IP. In mobile IP, the same agent and the same protocol and same they are actually coupled together. That is one big issue, or one of the issues which gives rise to a lot of the problems. So if we could decouple the location management from the handoff, then a lot of the problems actually go away by itself, and we don't have to do anything to solve all those issues I just mentioned before. So we said we need to develop a protocol where the location management and the handoff will be decoupled. And after decoupling, we will do the location management and handoff in parallel to data transmission, which means we will not lose data and the latency would be gone. The handoff latency we have seen 10-12 seconds, that will be gone, because we will do data transmission in parallel to location management and handoff. Whereas in mobile IP, they're done sequentially. And as I've explained before, when the device moves from the home agent to the foreign agent, first of all, there's a registration procedure, then handoff procedure, all these things happen, and then the data transmission starts. So we want to do all this stuff, location management and handoff, in parallel to the data transmission. That is one of the objectives we had in developing this protocol. And the other thing is the mobile IP works in the network layer, which does not worry about the performance issue of data communication. The network layer mostly is responsible for moving packets from point A to point B. It does not look at the performance issues. The performance issues are looked at by the transport layer, which is responsible for moving data between the end hosts. So if we can come up with a solution, a mobility management solution, which will be at the transport layer, then we can integrate this mobility management with the performance of the transport layer. So everything will be in one place. So in order to...
I'm sorry. I think so. Is that okay to ask question?
Sure.
Okay, all right. And also somebody, actually ask in a private chat, if they can ask question. Please, if you have any question, you can interrupt and ask, I take any question. So my question is, So, when you go from home network to the foreign network and all, it doesn't happen, instantly, right? In our regular example, you go to a different hotel or in some other city, that happens, and you open up your laptop, it might take some connection time, 12 seconds, whatever. It may not be a big issue, when you start, but if that happens, in the middle of an application you run, service, then it's a problem. So can you elaborate a little bit more on that interruption, 12 seconds, where exactly that's a big problem? um, in a terrestrial, it can happen when you go from one area to the other area. In the middle it can happen, but if you go from one city to the other city, you open up the laptop, how big of a problem is that? But when you compare that one now with the satellite connection, maybe that may be a bigger problem, because when the satellite moves, that's probably instantly it's going to happen. Probably if you can elaborate the significance of the problem, that'll be great. Thank you.
Okay. If we are browsing, we can easily stop the browsing and go to a different place and then start the browsing. That's what we are doing. The first example you gave, we go to a hotel and then get a new IP address and then start working again. But if you are watching a movie or talking to someone and you need to hand off from one point to another point, at that point you cannot tolerate a 12-second interruption. So that's one example. In the case of satellite, when you're downloading data, and this is probably real-time data, and it could be voice communication, or it could be real-time disaster data, or it could be data coming from battlefield, and these are instructions to the commanders, right? Or the commanders are giving instructions to soldiers, right? So at those times, you cannot tolerate those delays. So we're talking about real-time applications where the handoff has to be seamless. That's what I mentioned earlier, that the handoff has to be seamless. When you're moving to a hotel, the handoff is not seamless. Actually, that's not a handoff. When you're going to a hotel, that's not a handoff. You're just starting a new connection. Does that answer your question?
Yes, but my question is, like, when exactly that happens? You go from home network to the foreign network. Um, does it happen on the move?
Yeah, that's what, for example, if you are watching a movie and you're in the car, and if you are moving
Okay,
from,
okay. So it's you are in the train or car or something like that.
correct.
Okay, all right. Okay, makes
For
sense.
example, I mean, you can we can also relate to this, to the voice conversation in a cell phone. When you're talking to someone and you're driving, we are being handed off from tower to tower, and we don't want the call to be dropped. We want the seamless handoff from tower to tower.
Right.
So
That's probably, that's already, the cellular has made it to
correct,
work within, few milliseconds or few tenths of millisecond. Yeah.
correct, and that's the sort of thing we want to do for the data as well.
Okay. Thank you.
Okay, so in order to implement our proposed solution at the transport layer, we have been using the stream control transmission protocol rather than the TCP. So that is one big thing we had to change. And I will discuss the advantages and disadvantages of using the SCTP protocol. The SCTP is a standardized protocol, is a standard transport layer protocol. It's not something we developed as RFC, you can see that. And it has a feature called multi-homing. That means you can have multiple endpoints uh, in a communication, which TCP doesn't allow, and we are going to exploit that for seamless handoff. So the basic concept we have is we are going to use SCTP for communication. So here is a remote computer which is connected to the wireless network one, let's say the home network, and the device is accessing is communicating with the remote computer through this Wi-Fi or whatever access point it is. And when it moves from this home agent to this foreign agent, it will get a new IP address. And after it gets a new IP address, it will tell the remote computer that I've got a second IP address. So the remote computer binds that second IP address to the association. So we don't call it a connection anymore in SCTP. We call it an association, because the remote computer is associated to this mobile host, and this association can be via multiple paths at the same time. which TCP doesn't allow. If you set up a connection in TCP, you cannot tell TCP that I have a new IP address or my other end has a new IP address. You have to actually break the connection and then restart a new connection. But SCTP allows you to do that you can add multiple IP addresses, which means you can communicate over multiple paths at the same time. And I just showed 2. Actually, it can be more than that. And this is a big advantage, because if you look at the smartphone we have, when we are sitting at home, I have the Wi-Fi connection, I have the cellular connection. Both of them are active, but I can use only one of them. I can use either Wi-Fi or I can use only the cell phone tower. I have to choose between them, but I have paid for both of them unlimited use. If I could use both of them, then I would be able to do communication much faster. But if you use SCTP, you can use that sort of stuff, and we have done that in our lab. That we have gone over multiple paths and communicated data over multiple paths at the same time. But we have to use SCTP because you have to add multiple IP addresses to one connection. So that is the SCTP transport layer protocol we have been using, so that we can have multiple IP address. And the reason we use this for handoff is, as I mentioned, when you move from the home network to the foreign network, we get a second IP address, we bind the second IP address to the association. And when the mobile host moves completely into the foreign network, we can tell the remote computer that the other IP address I had before is not functional anymore, so remove it from the association. So it will be completely smooth handoff without any latency, without any packet loss. The reason being, I actually make the connection first before breaking the connection. Whereas in mobile IP, it breaks the connection before making a connection. That's where the big difference is. Let me repeat that important point. In mobile IP, you break the connection before you make the connection. Here we are making a connection before we are breaking a connection.
Gotcha.
And the example I give to a lot of my students when I'm teaching this concept is, when you already have a job and you want to switch to another job, you don't resign and then start looking for a job. You first get the second job offer and then you resign, so that you have a smooth flow of money coming in. You're not there without money. So that's the concept. Make the connection before you break it.
I have a
Sounds
question.
akin to this sounds akin to the mobile assisted handoff that's used in the cellular system.
I'm sorry, David, can you repeat?
Is this similar to the mobile assisted handoff that the cellular system used a few years ago, where it would actually be talking to both towers, and then the mobile would say, I'm now talking to this tower, and drop it? The mobile actually assisted that process. So it seems that this is an IP equivalent of that.
Correct. Absolutely right. This is an IP equivalent to that. That's what I was going to mention.
I have a question about Elon Musk's approach with his satellites. Is he using this technology?
I'm not sure exactly. I haven't looked into his stuff, whether he's trying to do, how much mobility he's trying to allow, or how much seamless he's trying to do. I'm not sure. Actually, this is a good point. I have to look at his stuff.
Because he has an antenna, as I understand it, that actually moves. So you mount it on your roof, and it actually does some sort of tracking physically and constantly, and then movement of some kind as the satellites go overhead. So I'm not sure how it works, but I've heard that.
Okay. So so just to illustrate where the SCTP stands, this is the typical networking stack. And you can see that SCTP is a standard internet protocol. It's not new. It's not something we developed. It comes standard because it has an RFC number, RFC 2960. And it sits at the same level as TCP, UDP, and SCTP. And the Windows machines and the Linux machines nowadays, they come bundled with SCTP, although we don't use it, but it's already there. The feature we are using, as I mentioned, is multi-homing. That means you can connect to 2 or more networks at the same time. You can have multiple IP addresses at the same time, and you can use all those multiple IP addresses, those multiple interfaces concurrently in one communication. That is one big advantage of using the SCTP, and we've been using this for the handoff purpose. So again, the concept is association rather than connection. So it's called SCTP, association between two computers A and B. And computer A and B both can be connected to multiple networks, and we can communicate over both the paths. And the association between computer A and computer B has two connections through two different networks. So let's look at how the signaling will work when we're doing mobility management using SCTP. So in this particular case, the device on the satellite is connecting to the ground station and sending data to the scientist. And when the satellite moves, if it comes under, if there is another base station under its footprint, it will get a new IP address, a second IP address, and it will tell the remote host that I have now two IP addresses, the old one and the new one. So communication between this computer and the satellite will be on both, or will be through both of these ground stations. And since the satellite is moving, at one point it will lose connection with the previous ground station, the first ground station. At that point, it will also tell the location manager what is the IP address. One thing is required here in this particular case, a location manager, because this mobile device is having multiple IP addresses at multiple times. So if someone wants to communicate with the device, how does it know what is the current IP address? In the case of mobile IP, we do not need that location manager because we are always sending packets to the home network, and the home network serves as a location manager. But in this particular case, we have to have a separate location manager where we will continuously update our IP addresses through which our current IP address, because our IP address is continuously changing. And at one point, the satellite will be losing connection with the original ground station, and only communication will be through the second ground station. And at that point, the satellite will also tell the computer on the ground that the old connection is gone, so delete it from the association. Now there have been, so when there are two communications going on in SCTP, you can say that this is my primary network and this is my secondary network. So when you are moving to the new network, you set this as primary, and then you can say this is a secondary, and then you can actually delete that connection also from the association. So this is a completely seamless handoff. There is no interruption because we are communicating over both paths at the same time before we are actually handing off. Some people say we need a different device called location manager, and that's not an issue because we can use the DNS as a location manager. And big companies like Google and Yahoo, all those people, they use the DNS as a load balancing mechanism. Basically, you direct people to different servers at different times, sort of. So they use it already, and we can use the DNS as a location manager as well to update our location. So this is something we did, which was a real experiment, which was sort of very impressive. That we were inside the building connected to the wireless LAN, and we also were connected to the Sprint network, the cellular network. So at one point, we started moving out of the building, and we told the correspondent node that I have got a cellular connection now, and here is the IP address. So we're communicating over both the connections. And as we moved out of the building, at one point we lost coverage from the Wi-Fi network, and all our communication was through the cellular network. And this was a demonstration we did using University of Oklahoma's wireless LAN system and Sprint network. So these are two real operational networks. And we could do the handoff from the Wi-Fi to the cellular network transparently without telling our university IT people or without telling the Sprint network people that we want some facility or we want some device. Nothing. We could absolutely do it from our end. As I said, the reason being we are doing all this stuff, this handoff, at the transport layer. So whenever we are at the transport layer, we don't need any help from the network infrastructure, because transport layer is end-to-end. So that made our handoff smooth, no packet loss, no delay. We don't need to tell the IT people, and we could do the handoff completely independently, smoothly, absolutely no problem. The only thing was, when you move from the Wi-Fi to the cellular network, of course, the data rate went down, which was expected. And this I'm talking about 7-8 years back, when the cellular network speed was slower than the Wi-Fi. I mean, nowadays we know cellular networks, a lot of them are much faster than the Wi-Fi. So that was the vertical handoff experiment we ran. And we could, if we wanted, we could also move to a satellite network coverage like a mountain, although we did not do it, and it will still work, because the principle is the same, that we will go through the satellite network also. So the very first thing we wanted to do was to test this philosophy with the same experimental network. So we set up a network in the lab with 2 access points, and we had a mobile node and a trolley, and we pushed the mobile node from one access point to another access point. And these 2 access points were connected to different networks. We had a home agent running and a foreign agent running, and that's our departmental network. And then the corresponding node is somewhere here. And we had, so this was the mobile IP testbed, the typical mobile IP testbed using home agent, foreign agent. When we're doing the Sigma protocol, the one we developed, we did exactly the same thing, except that we did not have the home agent and the foreign agent. We just had the access points. So these were just gateways between this network and the CS network, but it was not a home agent or a foreign agent, just normal gateway. And you can see we used exactly the same hardware, same networks, everything is the same, except that we did the handoff twice, one using mobile IP and once using Sigma protocol. And the Sigma protocol we had running on a Linux machine, and there was nothing special we did in the Linux environment, because the SCTP was already there. The only thing was we were running the SCTP protocol rather than TCP protocol. That's the only difference we had. So just to show you the very basic result, this was handoff using mobile IP. So with time, this is the throughput obtained at the this is the throughput obtained in the communication, and the throughput varied a lot. And this was because we were using an operational network, and also the TCP congestion control kicked on and off. People started downloading, stopped downloading. So these are the normal fluctuations because of the operational network and because of TCP congestion control behavior. And you can see at one point, I just put a red bar over there. At this point, the communication was completely zero. There was no communication. This was a time when the handoff took place in mobile IP. And we got it from the log that this is a time when the handoff happened. And you can see there's about 10-12 seconds of delay when there's no communication at all. With the same hardware, we did the handoff using SCTP. And this was the throughput. And as you can see, all these fluctuations are due to normal TCP congestion control, due to normal operational network, because we're using operational network, all this stuff, people starting communication, might be the stopped communication, all sorts of things. But if I ask you without the red line, where do you think the SCTP or the Sigma handoff took place? And a lot of people say, oh, probably here. And some people say probably here, but actually it took place here. But this is what we found from the log, that the handoff took place between these 2 points. And you can see that communication, you can see the throughput did not drop a bit. And the reason is obvious. It's not magic. It's not unexpected, because we were communicating over 2 paths, and we just switched to the second path and switched out the first path. So the user was not even aware the handoff took place. So that was the very basic. There's a very basic graphs we show people to say that what's the difference between the handoff using Sigma and what's the difference between handoff using Sigma and mobile IP. And remember that these two are based on completely different philosophy. One is at the transport layer, Another one is at the network layer. And when we're doing this on an experimental network with NASA, they go by TRL, and most of you who work with industry probably are familiar with this. And those are the TRL. So we implemented our stuff. Well, first of all, we did modeling and NS simulation, and those helped some students to graduate. Of course, we are university environment, and we implemented our prototype with a Cisco router in our lab. And then we implemented in the space hardware which NASA has. This is real hardware from a real operational satellite, and we implemented our algorithm on a real hardware which is actually in the sky, but we have got a copy in NASA. So we did the actual experimentation in real space hardware which is in flight in space. So we went up to TRL6, which was quite a bit of achievement for a university to develop a technology up to TRL6, because as you know, in the academic environment, a lot of the research actually ends here or might be maximum here. They develop a prototype and then it ends here, but it's hardly ever tested in a real hardware or a real environment, like in a mission environment. So we tested it on this single board computer. This is from Surrey Satellite Technology Limited. They have a constellation of satellites up in the sky, and this single board computer, they call it solid state data recorder, and it has a power PC which is very, very old and hardly has any power. All this is called power PC. It's so slow, and it runs an operating system called RTEMS, and it has very limited memory. And if you look at the real hardware which are in mission, think of the hardware in space in operation, or think of hardware in the tanks, or think of hardware army uses, defense uses in the warfield. They are not very modern operating systems. They are very old operating systems, but they work. The important thing is they work. They don't fail. In those mission critical environment, you cannot afford any failure. So they use operating systems which are very well tested and that contains only the very basics. So when we want to implement this on a space hardware, we found that the network stack doesn't have a CTP. The network stack doesn't have a full implementation even of TCP, because they just have the bare minimum. And that's okay, because in a satellite, you don't have a keyboard, you don't have a monitor, you don't have mouse, you don't have USB flash drive, USB interface. You don't need any of those. All you need to do is capture data from the devices, from the equipment, and process them and transmit down to Earth. So when we want to implement this, we found a lot of issues, because this is very low power, very low small memory, and the very old operating system, bare minimum operating system. So in order to implement this, we had to put in lots and lots of stuff in this operating system in order to make our system work. So one advice I give to a lot of people who work in the university is, if you want to work on a mission, in a project which is mission oriented, not just for theoretical research, not just for PhD or masters, it has to implement a mission. Look at the hardware and software available there in the field at that time, because we are in the university, we are used to developing very sophisticated algorithms on very sophisticated operating systems and very sophisticated machines, but none of those are required in a real mission, and those are not even available in a real mission. And I've spoken to people who in the DoD, and if you look at the hardware they use in the tanks, for example, they are very basic, doesn't have much power, but they work all the time. They work in extreme heat, they work in extreme vibration, they work in dust, moisture, everything. So that's a different scenario. So I always tell people, look at the stuff available where you are going to implement it. Look at your target system first before you start implementing your state-of-the-art algorithms, because those may not be usable there. So let me conclude this talk saying that satellite is going to be a very critical component in the global coverage scenario. And as soon as we go to satellite, as I mentioned earlier, mobility is going to be a big issue which we need to solve. It's not a new issue, but that's an issue we need to solve to make the network more efficient. And that's the last one, pay attention to the target system before developing protocols for systems which are in mission. With that, I will stop at this point, and I will acknowledge, I must acknowledge a lot of people who have been working in this project for quite some time. Some of these people are or were graduate students, they graduated, master's, PhDs. Some people were sabbatical visitors from other universities. And of course, these are the people whom we work with at NASA and Cisco in this particular project. So thank you very much, and I'll stop here. If you have any questions, I'll be happy to answer. And again, it's a real pleasure talking to you guys and share my research results. And I'll be happy to answer any question you might have.
Thank you, Eric. It's a very good talk. I have a question. So it's the Sigma protocol that you have been developing for a while, and can you say something about, what is the status? Did you take it to IETF, or did anybody adopt?
Okay, our main customer was NASA. That's for whom we're developing. And when a protocol has to be implemented by NASA, we went up to TRL 6, and if we want to go up to TRL 7, that requires this protocol to be implemented in experimental hardware up in the sky, not operational hardware, experimental but operational. And the SSTL satellite we're using for this, SSTL stands for Surrey Satellite Technology Limited. That's a company in Surrey in England. Their satellite has two components. One is the operational part, another component is experimental. And that's what NASA use for experiments. If we have to implement our one up in the satellite in the sky, then it requires help from the manufacturers of satellites. And that involves a huge amount of money. It's not going to be anymore that NASA gives us $500,000 and develop all this stuff. In that case, it will be millions and millions of dollars. Before NASA invests into this, they will try to make sure that this is the system they will implement, because they will have to spend a lot of money to work with the satellite companies. And at that point, they say that we don't have that much of money to go to TRL 7 or 8 with this protocol at this stage. So
follow-up question. Sorry. Yeah, this is Suma. Yeah. So are you hoping to actually drive it through standardization and get it through maybe a technical body to actually ratify it as a adoptable standard or a protocol like IETF 3GPP or any other bodies there for a wide adoption?
I haven't tried it.
Is it something that is planned, or you're just working with NASA at a experimental level and that's it?
We are working at the experimental level. As a university, we're not good at all this standardization stuff.
Okay.
And I've been to IETF meetings a couple of times, and I found myself completely lost, honestly, because there are all these big companies who are trying to standardize stuff. So unless there's there are other companies who are involved in this, who want to standardize it, or at least submit it for standardization and push it through. At the university level, we are not able to do it, actually.
Yeah. Okay.
That's not our core business at universities. And also, we don't know the technology. We don't know the know-how how to do it.
I mean, basically, you need some commercial backing. I mean, some companies to back you, like manufacturers and stuff like that, to take it forward. Okay.
Correct.
All right.
Correct. And also, the university doesn't put much thrust on standardization, because we are a different type of business. Our university thrust is mainly to develop new technology, publish it, let people know so that others can use it. When it comes to commercialization, when it comes to standardization, universities don't do a very good job, unless it is one of the very top universities like MIT, Berkeley, that sort of places. They are, or Cornell or Stanford, they are very much into this sort of stuff. But our university probably is not that interested in this sort of stuff.
I have another question. My name's Ed Metzler. I'm an IEEE member. I'm retired. I used to work at Intel a long time ago. So I want to return a little bit to the Starlink, and then there are others. I think Amazon and others are also trying to put up low Earth satellites that are going to fly around and put up for consumers to use. And it seems like it's the same problem, is it not, that they have with what you're talking about as a solution, that they have satellites that are many satellites that are going around very quickly, and people have to switch from satellite to satellite to satellite to satellite from their home. Is that correct? Is that the same problem that you're solving?
Yeah, we are trying to solve the same problem. Whenever internet access is required, or whenever we are using internet protocols in the space, we come into these issues.
Right, and I just wonder if all of them have invented their own solution to it with different protocols that they invented independently, or whether they thought at all about going with an internet protocol, because it would make sense to me to go with an internet protocol. It's intuitively obvious, right?
Yeah, a lot of these satellites are actually for internet access, but how they're doing the mobility management, I've tried to probe some of them, but it looks like they're secret.
Yeah,
they're not very open to it.
Yeah, I did a search over the internet real quickly here, and I didn't see any answers. Anyway, just throwing that out. Sorry.
Yeah, so it might be proprietary solution which they're not willing to share openly unless we have a non-disclosure agreement and project with them.
Yeah, it would be nice for you to share notes with them. That would seem to be a nice conversation. Anyway, bye-bye.
Thank you for the question.
So do you think this applies or might apply to the high altitude platforms as well, like the balloons, like the loon projects from Google's and those guys? You might.
Of course.
Okay.
Yeah, sure.
Okay.
One other question, I think. 3GPP has been studying this problem. They call it, I think, NTN, non-terrestrial network. Are you familiar with that, or do you have any comparison with that?
I am not very familiar with that.
Okay, in 5G, in the last few releases, they studied that. Now currently it's going on in the specification. They are standardizing few things in there. One other thing is
what is it called?
NTN, non-terrestrial network.
Okay.
Basically, the satellite or balloons and things like that. For that, all those handover and all those things probably they have looked into.
Yeah, I should have looked at that.
There's another. So you compared Sigma with mobile IP. There is another thing that 3GPP has studied. Something called interworking network or something. That what they have done is like a base station has both Wi-Fi and cellular, like the one example that you had in the university. Or it can be co-located, or it can be non-co-located. In that case, how do you do these, break before make and all kind of things, so that you have a seamless handover and things like that. I wanted to see, are you aware of that, or do you have any comparison with that kind of things? They probably have very, seamless handover, but that happens in the very low layers. Compared to what you are doing in the transport layer. So just see, do you have any comparisons for that?
I did not look into those. The reason I was trying to avoid the physical layer and the MAC layer and the network layer, all these things, I need the help from the network infrastructure. But I was trying to do it. I don't care about what network infrastructure you have. I can do it under any platform. So that was one of my main objectives, that I can, if you remember, I mentioned earlier that I want to be able to do it without telling the operators anything. So that is what That is how mobile IP does it also. Whatever the underlying infrastructure is at the physical layer, they don't care. As long as the IP layer is there, and every device is IP layer, that's a common layer, they can do mobile IP. And we said that we will go one layer above so that we don't even have to talk to the network operators, because at the network, whenever we do something at the network layer, we have to talk to the network operators. Like mobile IP has to have a home agent and a foreign agent. I mean, when I looked at all these technologies, all fantastic technologies which have been developed for internet, and a lot of these very nice protocols have not been implemented or have sort of failed. One of the reasons I found out is they have something in the protocol, something in the algorithm which needs to change the internet infrastructure. Internet infrastructure is so big that it is extremely difficult to change it unless there are 2 or 3 factors. And one of them I figured out, you can change the internet infrastructure if there's really a need that you cannot do without it. And if you can do without it, you will not change it. A good example is IPv6. It's a fantastic thing. We don't use it because we came up with other solutions, NAT and all those stuff to solve the IP shortage problem. Then we look at differentiated service, integrated service, all these things. They're fantastic, but they all need the core to be changed.
Right.
So at the very outset, I started with saying that, okay, I'm going to develop something which does not need to be changed at the core. So if you must do it, then people will change the internet core. Or second way you can change it is if someone can really make some money somewhere, then it can be changed. There are 2 or 3 big things which need for the internet infrastructure to be changed. So I wanted to do it completely end to end. So one downside which I have not mentioned so far is any application you use for Sigma must use SCTP. That is one big downside of this handoff protocol. But the thing is, Sigma is already there. And if it is for a mission agency like DoD or NASA, we don't need to change too many hosts or too many computers because it's all under their control. So you can take all the applications for which they have source code and they can recompile it for SCTP. The only thing you have to do is change the TCP calls to SCTP calls at the source code and recompile the application. You don't need to change anything else. Only thing you need to change the TCP calls to SCTP calls. How long does it take? Okay, I put an MSc student, master student, to take a video server and a video client, a public domain one, for which we have the source code, and told him to change all the TCP calls to SCTP calls and run it over Sigma. And this master student was completely new to all this compilation things and calls and all this stuff. It took him 7 days to change the video server and the video client to make it work with SCTP over Sigma. But once he has figured it out how to do it, once he has done it, next thing he tells me that if he is given an application like this with source code, he can change it within 2-3 days.
So you mentioned the SCTP is available in many platforms, but not much used. Do you know any the adoption of that protocol compared to TCP?
No, TCP is such a dominant protocol, and it works fantastic. Nobody's interested in going to anywhere outside TCP. However good it is, there's not a need to go outside TCP. That's what I was saying earlier, that whatever you can develop a fantastic technology in the internet world, and people will not use it unless they have to. So people are happy with TCP and it works. So why go to SCTP or any other protocol? And when I say TCP UDP pair.
Any other questions from any other audience? Yeah.
Let's see if I can do a question here. First time I tried this. I'm wondering about authentication and spoofing and replay attacks. And now you're dealing with an entire world of people trying to break into your conversation through the satellites. And seems like that makes security very, very difficult for this.
Okay. The Sigma protocol is not going to introduce any additional vulnerability because we are working at the transport layer. If SCTP is secure, the Sigma is going to be secure. So we have not introduced any protocol at any of the layers. We're just using those protocols and made the mobility management as a transport layer application sort of thing. You can view it like this. So if you can break into SCTP, of course you can break into our protocol. But our protocol did not introduce any new vulnerability into the network or SCTP or anything else.
Okay, so you're counting on the more closer to the hardware protocols to protect what you're doing, and that makes sense.
Correct.
Have you considered any diagnostics you can put in the system so that you can detect these incursions that are occurring at the more basic layer, so that you can make sure that what you're doing will let the user know that there might be this issue coming up?
I mean, Keith, what was your last sentence? I think the voice is breaking up slightly.
Well, I set this up just a few minutes ago. So if you could put something in your protocol in your system to verify that maybe some of the lower level, more fundamental protocols aren't being exploited, then that might protect security. You're not in charge of those lower level protocols, but it would be nice for the unsophisticated user to know whether there are issues coming up.
Yeah, that's a good point. We haven't thought about it because we were more concerned about the mobility management thing and removing all those 5 or 6 disadvantages or limitations of mobile IP. That was our main concern. And also to make sure that it works in different networks like Wi-Fi, cell phone tower, everything, so that people on Earth can also use it, not only for space. Because one of the objectives of mission agencies is to have return on investment of taxpayers' money. So whatever money they spend, they want to make sure that some of it can be used, or most of it can be used, or a lot of it can be used by the taxpayers, because the taxpayers want to see the return on investment. So, and previously, one long time back, 50 years back, these mission agencies had a lot of money, and they could develop everything from scratch based on their needs. Now with money being tight, they're trying to take technology which have been developed already and tweak it and see if they can use it for their own purpose.
Right. Any other questions from any other audience? All right. If there is no other question, let's thank our speaker for a very interesting talk. Thank you, Adik, again, to spend some time with us, the Oregon chapter, and give a good talk. Thanks. Thank you, Adik. Pradeep, do you have anything?
No, I concur with everything you said, and thank you again for a very engaging presentation today. That is not, it is a half and half sometimes, and you did a very good engaging conversation today. So I like to congratulate you for that, and thank you again for the rest of you who spend a late Thursday evening listening to this discussion. Thank you all and have a very good evening.
And thank you very much, Pradeep and Rath, for organizing this and inviting me. It was a real pleasure to be able to tell you guys what I'm doing for the last few years. And thanks everyone for attending. If you have any question, feel free to email me. My email address is atik@oe.edu, but nowadays you can just Google my name, it will come up.
Okay. All right. Thank
Thank
you
you
all.
very much.
All right.
Okay,
Thank you. Thank you.
Good night.
Good
Thanks.
night.
Bye-bye.